if I want to maximize a property, I want to predict behavior that no one's ever seen before. We're now sort of extrapolating into unknown space, right? If Amazon is going to make a book recommendation to me on an ad that they're serving, they typically try to find, they have like a profile of me in machine learning worlds that exists that says, oh, Chris is just like all these other people, serve him this kind of book, he's going to love it. But we don't really want to do that. We don't want to sort of predict that in material science. We want to predict something that no one's ever seen before. That's a very difficult task. So what we do is we incorporate some aspect of uncertainty.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And without further ado, let's get right into it.
Today's sponsor is MatMatch. With MatMatch, you can find materials for your projects in their free database of thousands of metals, polymers, composites, and ceramics. For example, you could search based on a given mechanical property, such as hardness or tensile strength, or simply search by name to find more information about a specific material. You could also find and contact suppliers if you have questions about a certain material, and join more than 2 million engineers and designers who use MatMatch every year. To join, simply go to matmatch.com and start searching for free today. Hello everyone, our guest today is Chris Borg, a research scientist at Citrine Informatics. Citrine Informatics is a software company focused on developing an artificial intelligence platform that powers innovation in chemicals and materials development. During his time at Citrine, Chris has managed various research programs applying machine learning to material discovery problems, developing specialized tools, and automating workflows to extract and manipulate materials and chemistry data. Chris also founded an undergraduate research fellowship program, encouraging students in material science and chemists to gain skills in data management and data science. We are very excited to learn more about material informatics and its interesting applications. So thanks so much for joining us, Chris.
Puneet, David, thanks so much for having me. Pleasure to be here. Very generous introduction.
Of course. And so we'll start with the basics. This episode will revolve around machine learning, AI, and its integration with material science. So what exactly is this idea of materials informatics?
Yeah, so materials informatics is sort of a catch-all term, I'd say, for data-driven methods, data-driven science, right? So I think in the past, I've definitely called it sort of data science for materials. And I think I like to think of informatics as sort of using data, and then whether that is, from past experiments or from physics-based simulations to sort of help us drive decisions on how we're going to develop new materials with interesting properties. And then, further, I think one of the ways that we most effectively do that is through statistical algorithms, machine learning applications. You probably hear that term a lot.
Yeah, so you kind of mentioned it there about like some of the specifics, but I think machine learning overall is a very nebulous term. That means a bunch of different things, especially in a bunch of different industries. Like Netflix and Amazon do a lot different machine learning than you do. So in the scope of material science, how would you define machine learning and what are its applications?
Yeah, it's interesting you bring up sort of Netflix and, are the sort of tech companies we traditionally think of as working with big data. I think one of the fundamental differences of sort of working on machine learning problems in material science is that we're typically very data limited in the amount of information we have available to us at any time. And that's because, experiments, simulations are cumbersome and expensive to run and record. And it takes a lot of time and power to collect this information. But maybe going back a little bit, I think, as material scientists, we're really focused on identifying relationships between sort of like property, structure, and process. I think we've heard that before. We sort of seen a little diagram. And sort of for ages, scientists have done this through sort of three methods. And they're sort of like doing experiments and actually like observing what happens and then recording that. And this is like the empirical laws that affect us. And then there's like physical models, like the laws of thermodynamics, right? And then we have recently come into this age of computation and have been able to do sort of like physics-based simulations, something like density functional theory, things that we couldn't previously do we can now do with the advent of computation, we now sort of come to, I think, the sort of advent of machine learning in material science has really been, let's see, it has been nicely classified as like the fourth paradigm of material science, where we now have this new age of sort of being able to do data-driven methods along with the other three. So we're still going to continue to do all of these other things that science has done forever. We just now have another sort of tool in the toolbox to help us understand these property relationships better, right?
I think you made a great point, is that with Netflix and Amazon, in my experience, like when we talk about big data, we're talking about billions and billions of points that always are updating. And just, if you think about your phone, it's the constant source of data. But I guess I never really thought about how hard it is to get data for material science, because someone has to do the lab experiment, collect the data, and just all those different things. So do you think as we move forward, data collection for material science is starting to see more importance in the field? Or do you think we're still lagging behind in that respect?
I think, yeah, that's a great point. I'd say that's going to be a definite we're going to see a lot of impact from that in the future, right? Mm-hmm. We're sort of recognizing, okay, if we want to have really nice training data sets that really uncover interesting properties, we really need to make data a first-class citizen when we think about starting to set up a machine learning problem. Mm-hmm. So just kind of like you said, I mean, these other industries have been working on this for a very long time, and they have really, really robust tools and software to help them collect, record, and manage their data. We've been starting to do that in material science, and I've seen a lot of great tools developed in the past decade. But I think, more importantly, that it's just getting started, right? We're sort of just on the forefront of all those tools and development, and they're only going to get better over time.
So then how at this point, so like David and I, we were in a computational material science class, and we were in a very simple model, H2O and like the coefficient of thermal expansion, right, David?
Yeah, that's correct.
CTE. And so even then, when we were trying to find literature data, it felt like it was so difficult to match that to the theoretical value that we found through the simulation. How have material scientists gone about finding what data is considered like good data?
Yeah, that's a good point. I think we always see that in terms of, how do I know when to trust a certain data point? Right. And I think we'll see the tooling around that get better. We're going to see more ideas around, okay, how do I, first of all, collect data that is going to work together? That is, if, the experimental conditions that you have in your lab and the experimental conditions that I have in my lab might be different. And we've seen this for a really long time in terms of just reproducibility. Maybe the humidity in my lab is 20% higher because, here in Portland, we're going through a heat wave, high humidity. The lab, that could really be a big difference, right? You imagine that these types of things are going to need to record along the way. That, I think, is one of the limitations we see from machine learning models now, where it's like, well, I have a lot of good inputs, but maybe I don't have all of them to describe that. Maybe no one was recording the humidity in the lab, and that was the one that actually controlled the differences between our two experiments.
I currently work for Equifax, and we have giant data sets, and one big aspect of creating a model is getting all the data ready. And one thing about that is missing imputation. So any value that's missing, we then have to create some logic behind how we want to score it. Do we want to drop the variable, that consumer? Do we want to add a 0 or 1? Something that creates a more defined data set, create the average. So I guess as we go into material science and we're missing some of these calculations that are essential for model building, we don't want to throw away all imperfect data because, as you said before, we're still working on our collection methods. How do we deal with missing imputation scores?
Got it. Yeah, I think you actually mentioned one of the methods that is, I would say is a reasonable choice, right? If you have a really nice data set, but you have to drop a ton of rows because you're missing one of the inputs, a great idea is to, can you just take an average and then impute an average score for that value, and now you can use the rest of that data. You don't have to throw it all away.
Yeah.
Right. These are some of the quick and dirty methods you see sort of researchers have been doing. I'd say down the road, we're going to start to see some more robust methods. But it also means that, there's no free lunch, right? Like if you don't record something and you don't know what the actual values are, you're not going to be able to use it. And I think we're recognizing that, and we're sort of taking a step further and saying, okay, how can we prevent this from happening? Do I have to go back to my literature review and now add a whole new column that is a new property that we weren't recording previously because we know it's important to, yield strength, for example, right?
Yeah, no, absolutely. And there seem to be so many parameters that surround this idea. So that leads me to the next question. When we talk about machine learning, it feels like it's popping up everywhere and it's being tried as a solution to all of humanity's problems currently. But obviously there are some limitations that we've already discussed that come with ML and AI. And so in the scope of MSc, in what applications can machine learning be particularly useful for, and what are the limits that we've seen so far with AI?
Yeah, that's a great question. I think, a lot of the limitations that we just touched on are sort of around the data collection itself, right? Is like sort of what is the data telling us? One thing that I think we didn't really necessarily touch on previously, but might be important to discuss is sort of, well, do we have a high dimensional problem to solve in material science, right? This is something that we always kind of want to ask ourselves as the first step. And then, okay, do you say, okay, hey, I have this problem. I think these are the controlling variables. If there's only one or two, maybe you don't need machine learning. I think one of the areas we touched on was data collection and it being really expensive, right? You might find that, let's say, for example, you're studying fatigue strength. Doing a fatigue cycle testing takes a long time, could take weeks. That's going to be really expensive, and you're not going to get a lot of feedback sort of during the process. You sort of have to wait for it to end, and then you sort of know how strong your material is. You might think, well, great, is there now like a surrogate property that is quicker to collect and gives me some indication of the fatigue strength? Maybe that's the ultimate strength or the yield strength or the elongation or some combination of those things, some combination of mechanical properties that are much quicker to collect. And then I could go sort of to that next step once I know I have something good, right? So from the ML perspective, you're looking for a property that you can measure that is, going to give you some inclination about what you're actually interested in, but that property is also something that you can measure that you can collect a lot of information about.
Yeah, I remember that story about the fatigue cycle. I think it was in one of my classes. They're saying GE or some other big company has this giant just warehouse full of fatigue cycles just going and going. I think it's been for like decades at this point, trying to create a really, really nice fatigue cycle for steel or something like that for like over like a couple decades. But one thing that you mentioned was, how do we like hurry it up? And so I've done battery research, and in that we call it forced failure, where we can't wait around to see what happens in the battery's 10,000th cycle. We want to fail within 2 weeks so that we can see what points are weak. And so what we did was we applied extra stress in the form of heat, in the form of higher cycle loads, such as like higher current. How can we manipulate the testing conditions to give us the data that we need to put into these models that you're talking about?
That's a great point. Is there a question? Or I feel like you've answered the question for me in a way.
I guess my question is, when we talk about this and we talk about forced failure, we can't necessarily say that it's going to be an exactly linear relationship, right? With like the like 10 degrees Celsius means like 10% worse like lifetime, right? There's some sort of mathematical relationship that will factor into these forced failures that we talk about. So as data scientists, do you guys have any methods to try to work out the mathematical relationship, or is that a problem that still needs to be tackled?
I see. Yeah. So if you're saying, okay, I have, a certain property I know I can measure, and there's a, sort of relationship to a property I'm more interested in, right? That is definitely something you could sort of bring into your sphere of modeling, right? Bringing in these relationships allow you to now sort of you're now combining sort of two of the paradigms, which is like the physical sort of empirical relationships, and now you're sort of data-driven machine learning methods, right? So I think that's a really nice method. We could talk about some other ways that works, but I don't know, I don't want to sort of go down too many rabbit holes here.
Well, I guess that kind of brings us into the next question, is that as computers become more powerful and more data is gathered, and the predictiveness and the accuracy improve, the things that we're talking about now, like how to like min-max things and like do these actual experiments, will there ever be a point where a computer could just do all this by itself and not need any input from humans to get the result?
Yeah, we've kind of been asked. At least I've seen this sort of question before in terms of, will sort of AI just completely sort of replace the scientist in the laboratory, right? Is a robot just going to continue to do everything autonomously, and then eventually we're going to sort of get some miracle materials out? And I think I've heard this example, and so I tend to use it a lot because I think it sort of exemplifies really well where the field of materials informatics is headed. And so, back in the 90s, IBM developed the supercomputer Deep Blue to sort of play chess against like grandmasters in chess at the time. And so it was sort of pinned against this grandmaster, Garry Kasparov. And so while it in that first set of matches, it doesn't win, but eventually it does. And so in the late 90s, Deep Blue beats Garry Kasparov at chess. And that's sort of like a milestone in sort of computational development. I think that sort of was really impressive from a standpoint of computation, right? And so I think at that point, that same question is kind of asked, right? It's like, well, is chess now a game that is solved, right? Like a grandmaster is not going to continue to win anymore. But I think, it sort of takes a different path, and it's a really interesting one. There's this new variant of chess that exists now, which is called sort of advanced chess or centaur chess. And sort of in this variant, the computers and the grandmasters play together, where the computer sort of analyzes thousands of possible moves. And so the master sort of reviews those moves and then sort of chooses one of the moves from the results that they think is going to be the most advantageous to play in that particular situation. And ultimately, we see this combination of sort of, human and machine together being a very successful team. Often they tend to outperform both singular AI chess engines and other grandmasters. And I think this is the way that things are going to go for material science, right? We're adding sort of data-driven methods to a toolbox that already has a lot of good tools in it. And it's going to be up to you as a scientist to know when to employ those tools and how to employ them effectively.
So then what exactly will the role of material scientists be when, these machine learning methods continue to be more and more effective? So I know you mentioned it very briefly, like we have that creative mindset where we can choose strategies based on our own experiences. Can you dive into that a little bit in more detail?
Definitely. There are going to be, there are going to be plenty of examples where we're going to see that, the models are only as good as the data that goes into them, right? There are going to be things that they're not necessarily going to know when they want to make a certain prediction, right? You could easily generate a model that let's say connects like composition and a mechanical property. Let's say, we're doing alloy development, we're collecting composition and mechanical properties. We're giving it things like iron, we're giving it things like copper, aluminum, different alloys of those three elements together. And then you type in something like H2O. You're going to get a prediction back. The model isn't going to know that, well, the molecular structure of water is very different than something like, iron and copper together. Unless you, program that in yourself in a way, right? Unless you have a representation that is going to account for that. So I think that's the type of role that you continue to have to play as a scientist, is to know, sort of what are the types of things that the model is going to be good at predicting, right? Where it's like, it's going to be really good at telling you something like the difference between, copper and iron alloys, if you train it on that, versus you as a scientist understanding that, okay, a water molecule and an iron alloy are very different materials.
Absolutely. And so we've hovered around some of these examples in which ML has been used. So let's just dive into a couple examples about how, materials informatics actually has made a real world impact. And so in David and my basic chemistry classes, we've learned about formation energies with different reactions. And so maybe we can talk about that a little bit. Can you discuss how ML has been used to predict formation energies for various compositions and why exactly this is important?
Yeah, I think formation energy is a great place to start because it helps us understand how sort of, materials are stable under certain conditions. What are the types of materials that exist in our world naturally? And what are the types of materials that we can sort of make that, if under the right conditions could form, but they just haven't happened in real life. Yeah, right. And so I think, this also coincides with sort of one of the first major impacts of ML to material science. So you mentioned I work for a company called Citrine. Our chief scientist, Bryce Meredig, wrote a really nice paper with his team at Northwestern to sort of look at this problem from a sort of the new perspective of data-driven material science, right? Mm-hmm. And so the first thing that they do is, they say, okay, well, we want to find a bunch of materials that don't exist yet. How are we going to do that? And one of the ways that you can look at that is to say, okay, well, we can calculate formation energy using physics-based simulation called density functional theory. I was an experimental chemist before I came to Citrine. I'm not an expert in computation. I don't know a ton about DFT, but from what I understand, it is a reasonable surrogate for giving you some information about whether a material is going to form under certain conditions. Great. They now say, okay, well, we can construct a large database of these energies, and then we can train a model to sort of connect now the composition to these formation energies. And then it turns out, doing that and then making predictions is really quick. So you can actually make thousands of predictions all in the same day, where you could only run, maybe a dozen or a couple hundred DFT calculations in a day. Mm-hmm. So this now looks like a really great screening method for finding the right compositions to test via new DFT calculations. And so they use a machine learning model to make predictions on a large set of unknown compositions that have never been tested before, that have never been run DFT on. And then they also combine their intuition and they say, okay, great. Now we have all these formation energies, but let's look at the list and pick the ones that we think are actually going to be, physically reasonable based on sort of the empirical rules we know. They say, okay, which one's charge balance? That's a really great way to say if this is like, an inorganic material is going to form. If it doesn't charge balance, it is really unlikely that you might have something that's going to form, right? So they pick about, I think it's something like 8 or 9 of them that charge balance. And then they go and they run a DFT calculation on and they say, oh, wow, this actually does work. It is stable, and it like the machine learning model predicts it to be stable and the DFT calculation now predicts it to be stable. We hadn't previously thought of these compositions. So it's cool. It's a really, really cool way. I think that was kind of the big impact and said, oh, wow, look, machine learning can be applied to material science in sort of a new way. Where else can we do it? And now we've seen sort of since that was published, there have been fields, not just in computation, but like in experiment and other areas where, using machine learning for materials discovery has been very effective.
Yeah, I think that's a really cool story, especially just because when we think about what's the new best thing, we had an interview recently with a guy who takes new materials and turns them into a new product. But the big question we have for him is, how do you choose your materials? Mm. And it's always a question of how do we improve upon the past? And materials are really crazy and they kind of form randomly sometimes. So I think it's just a really cool story of how there are ways that we can kind of sift through thousands of ideas to find some that are actually could be viable.
Yeah, right. And I think the important aspect is that could part, right? Is that we never have complete confidence in a statistical model, right? That's sort of the crux of it. And that it's still, as a scientist, you need to really come to the table with a good understanding of what the problem is to make some educated decisions around how to best effectively use that model. So I think that's a great point.
Mm-hmm. Mm-hmm. Yeah, I think that's a really great story. And the second case that we had talked to you previously about was with organic semiconductors, where new semiconductors with high hole mobility were found through the use of sequential learning. So first, could you explain what sequential learning is? And then could you kind of tell us how we applied it to find new semiconductors.
Yeah, so this is definitely not going to be the only example of sequential learning we can talk about.
Mhm.
But sort of sequential learning, it's in other industries and in other areas of material science even, it's called active learning. It's sort of when you have an initial machine learning model and you do sort of a first round of experiments or computation to verify that's like an example we just said. They have a bunch of predictions, they test some of those predictions. Sometimes they're, I mean, right, oftentimes you would hope, oh great, these are going to be right all the time, great. And then a lot of times they're not right, and you say, oh, what did I do wrong? Well, maybe you didn't do anything wrong, maybe it's just that the information that you have at the time doesn't reflect the actual problem well enough, right? So what you can do is take that information that you just got from your experiment or your simulation and add it to your model, right? Now you have more information, you add it to your model, you update that. You've now sort of created this cyclical nature of experiment where you work with you work with the machine learning algorithm to make predictions, you test those predictions, you put the data back into the model, and you do the cycle again. Ideally, the model is going to improve over time and sort of capture the reality of the situation better.
And when we talk about sequential learning, it almost sounds like evolutionary neural nets, where they run simulations and then they take the best actors and then they replicate that and it's sequential through that way. When we talk about sequential learning in material science, how do they like select what to test? And then do they throw back in with the old generation of data and like they scrub like what we know now? Or how exactly does that work?
That's a great question. I think that's definitely an important area of research that is currently being conducted. You can imagine sort of there are many ways to decide how to test your next material or which material to test next. The obvious one we talked about was using your intuition, right? But let's say now we want to be more rigorous, right? We want to be more scientific about that. There are a couple methods we can employ. These are, I've heard them being called, various acquisition functions, right? They sort of help you decide from a list of predictions which one to choose out, right? And so let's say in our example we're going to maximize fatigue strength, or we're going to maximize hole mobility. If we're going to maximize a particular property, one acquisition function might be to take all your predictions, sort them by the value that you're predicting, and then pick the highest one. That is what we call like the exploitative approach. You're sort of exploiting the model to say, give me the one that's going to be the best. Let's not think about it. Let's keep continuing down this train. Okay, but we also know that incorporating an aspect of uncertainty in machine learning is a really important thing, especially for material science. And I think this is something we haven't touched on previously, but it is a way that material science is different than traditional machine learning methods, in that if I want to maximize a property, I want to predict behavior that no one's ever seen before. We're now sort of extrapolating into unknown space, right? If Amazon is going to make a book recommendation to me on an ad that they're serving, they typically try to find, they have like a profile of me in machine learning worlds that exists that says, oh, Chris is just like all these other people, serve him this kind of book, he's going to love it. But we don't really want to do that. We don't want to sort of predict that in material science. We want to predict something that no one's ever seen before. That's a very difficult task. So what we do is we incorporate some aspect of uncertainty. Incorporating that uncertainty allows you to now have new acquisition functions that says, okay, how certain am I that this predicted value is true? And so you could say, okay, well, if I want to make my model better, maybe I should test all the things it's uncertain about first, right? So, and that's the sort of more extrapolative approach, right? Where you're saying, okay, let's explore new areas and say, when we explore those new regions, we're now going to eventually understand them as quick as possible. And then we can sort of, maybe that's going to be most effective. And then sort of a third approach might be a middle ground, something right in between sort of the exploration and the exploitation, where you're saying, okay, I still am interested in something the model thinks is good, but what about this aspect of uncertainty? Maybe there's something that because it has high uncertainty, is actually potentially better than one that has low uncertainty and is predicted to be really high. So that there's sort of a trade-off there. And I've seen this in various papers. The way that they make this trade-off is different. Sometimes you like set a discrete value, sometimes it's kind of continuous, sometimes it's somewhere in between. But yeah, it's an active area of research. It's really interesting. I could talk about it ad nauseum probably.
Okay, so then this might require maybe a very technical answer, but when we're trying to push boundaries and extrapolate, then what type of statistical analysis is involved to or calculate that uncertainty, since we aren't operating in a realm that we're comfortable in?
So there are various methods for calculating the uncertainty in a machine learning prediction. I am actually by no means an expert in how to do that, right? So there we use sort of standard off-the-shelf statistical methods that help us do this. So we're very fortunate to exist sort of in this world where, the statistics have already been very well studied. And so we can sort of rely on these methods developed by, statisticians that we can apply to material science rather than having to develop sort of our own methods in a way.
And I guess for personal experience, when I built some models to model like who wins the NBA game, one thing that I noticed is that I can just throw in random different packages online. Like I can use different optimizers, which is like how you create the functions. And is that just what you guys do? Do you try just like, let's try this one and then let's try a different optimizing function and like try a third one to see the differences and see like maybe who are the most variant? Or is that something that maybe is a little bit more frowned upon because it's not as scientific and it's more just throwing like darts at a dartboard almost?
Yeah, I mean, I think it's going to be problem specific, right? I think if you have a good understanding of what kind of problem you're interested in solving, if for example, you can maybe do some kind of testing beforehand to kind of understand, do I think there is a linear relationship between these variables or a non-linear relationship between these variables? If you had some inclination on that, that might help you choose the type of machine learning algorithm you were most interested in. I'll say this, I've found that while the choice of algorithm depends sometimes, there are times when it may not depend. And it's much, much more important to have a good understanding of the data that goes into it. I think, again, we sort of come back to this idea of, materials data kind of being sparse and messy and not really capturing the full problem. The data that you put in plus the way that you represent a material and machine learning space, I think are the two key components that are going to be way more critical to giving you a sort of strong foundation for a machine learning experiment than the choice of algorithm you use.
And so, I know maybe you're not allowed to talk too much about the projects specifically, so I just wanted to talk about maybe the process in a little bit more detail. If someone comes to you saying, hey, we want to design, a low thermal hysteresis shape memory alloy, then what exactly is the process of like collecting that data? And then like what types of information are you looking for that dictates what method you use?
Great. I am fortunate in that I can speak to some of the things that I've done with Citrine on some of the programs that we work with academic groups. So you mentioned shape memory alloys. I might change that a little bit. And let's say there is a program that we're interested in developing sort of new, like designing high entropy alloys for, high temperature applications. One of the main things that is really interesting here is that they want to design high entropy alloys they want to design alloys that, one, have high strength, and two, high ductility. They also want that because those typically aren't necessarily aligned. And they need to operate them at high temperatures if you're like in a jet engine or something, right? So one of the first things we did when we started working on this was to collect a bunch of data, right? As you might do when you're doing machine learning. And so we started to collect a lot of data, and we found like, great, there's review papers here and there, we're starting to put them together. We're starting to look at certain trends. And then eventually this became such a big a big sort of piece of the puzzle here, that it went all the way to like, okay, we should develop a sort of new database that combines all the data sets together, that can eventually sort of be our go-to source when we want to pull out information to start to study these high entropy alloys. And so that was a whole publication in itself, just focusing on building the data set.
Wow. So I guess then that leads us to talking about the future of this field. And so like, we've already talked about how it's a challenge to find reliable, useful and applicable data, because there's that combination of experimental and computational literature in MSE. And so I was just wondering, could you talk about the main challenges that this field is facing, and also really the steps that are taken currently to address those challenges?
Mm-hmm. Yeah, I've only been really studying informatics for maybe 3 or 4 years now. And what I've seen, even in that short amount of time, is that the sort of tooling around data collection and standardization has come a long way. But I still think there's a lot of work to do, right? There is not necessarily one sort of standardized way to represent materials data. And that's because materials are very different, right? So representing them in ways that make sense to certain fields are going to kind of continue to develop over time. I would say, since that might be true, developing methods that sort of connect those different material schemas is going to be really important. Can you translate, a schema for, representation of a polymer material to something inorganic, for example? And should you need to do that, right, is a question, right? So it's like, maybe we don't need to do that if you just want to, if you're working only on polymer development, maybe that you only work in this one schema, right? Mm-hmm. So yeah, data standardization, I think, is a big topic and will continue to be one in the future. Let's see, other challenges. Another challenge, actually, that I would like to see more work on, and I'm particularly interested in, is how we represent materials to a machine learning algorithm. There's been a lot of great work in this, right? You can imagine, if you take like the periodic table behind me here, right? And you were to just create like a naive vector of all the elements, you could like put a compositionally weighted vector and say, okay, this material is H2O, this material is methane, this is an iron alloy. Well, now you kind of, that's great and a good place to start, but now you kind of have a problem, right? Like we said before, water and alloys aren't really the same thing. So what have we done? Well, there's been a lot of great work to say like, okay, now you can actually represent them by like their sort of atomistic properties, right? What is the ionization energy? What is the sort of weighted average of all the like densities of the elements and the volume of the elements? And so now you are actually bringing in chemistry and physics to the problem. And that's really interesting, right? So now you're saying, okay, well, now I'm teaching the model chemistry and physics. Continuing down that road, there's a lot, I think, that could be done that will really help us start to understand, start to be able to represent problems better, that will help, find new materials faster, for sure.
Yeah, one of my favorite stories when I was first getting into data science was that Google started collecting data for like years ahead of time and just collected it and didn't do anything with it because they could see the foresight. And one of the biggest reasons why Amazon's so big is because they have the most data. And just when we talk about materials, I feel like you've talked about this a little bit, but it's more data will always be good, right? But we're almost not doing the same type of data science. We are going to try to use ML to predict something new, something that hasn't been seen before. So when we balance the two of those, how do you see us overcoming, what are the hurdles we have to overcome, and how do you think we're going to overcome those?
I could see that's an interesting problem, because we always think, well, more data is always better. We hope that to be true, but you can imagine a situation in which you're incorporating aspects of, let's say you're incorporating a data set that is sort of incompatible, kind of in the ways that we talked about previously, where you're incorporating data from one lab and another lab all together, and we didn't record enough parameters. So now the model has learned something that isn't a good representation or realistic version of your lab in particular. So you might have been better off just using the few data points you had for your lab, right?
Yeah.
That's an interesting point. I think another point is that, we always say like, well, whoever has the most data wins in a way, right? You want to collect the most information, you want to have it, and then you can now do things with it that other people can't. I think there is a push in science, and especially with Materials Genome Initiative and things, to have sort of fair data principles, right? And sort of open reuse of scientific data. You can't copyright scientific fact, I've learned, which is great, because that means that the representations that you develop in a lab, you publish them, we can actually use that data to now help everybody. And so I think that's an important point too, when we start to think about who's going to own the data over time. We really want to push for there to be more open data sets. I think I touched on this too, is that it may not be the case that if you are a lab developing new polymer materials, that you even would care about data for high entropy alloys, for example. So if you had a database that had all of it, you may only want part of it. And so I think, again, there's some aspects of trying to focus on creating open data sets that have fair principles is going to be a really, really important aspect of the future.
And then I guess this is loosely related to AI, but are there experiments that are being done where we're automating that entire process so that those parameters can be set and there's less room for human error?
Yeah, human error is a good point. I recently talked to a friend at the University of Liverpool. I used to work in a lab, make materials, and I would grind up powders. I put them in the furnace, watch them. There's all steps in that are opportunities for me to make a mistake. They now have a robot that can do a lot of that, right? So it's really, really interesting to see things coming along. It can weigh out the powder, it can mix it more appropriately, it puts it in the furnace. It could do, probably a lot of the steps we can now take out of the equation. So while it, we can start to see those types of steps in automation happening, I think we're still going to need the guidance, right? To set up the experiments, to do the right ones, to understand what's happening. But I think that's just a great sign. Things are getting better across the board, right? Is that well, okay, great. Now I'm not sitting in the lab for 10 hours a day making powders. I have to go to bed at some point. The robot doesn't have to sleep. We can just plug it in and it's going to work, right?
Absolutely, absolutely. It's the idea, again, of this centaur mentality where humans and computers are working together to just be more efficient and save time or just make more educated decisions, it seems like.
Yep.
Cool. And so we can kind of just wrap this up because you've told us a lot of these applications, and we've heard time and time again that ML and AI will play very important roles in MSc. So what advice do you have for those who are interested in pursuing a career in material science as it pertains to taking advantage of these machine learning tools, and how can we incorporate these into our toolbox to differentiate ourselves in the job search?
Yeah. So as far as, for if you are maybe studying chemistry or physics or biology or something, right? Some physical science, and you want to incorporate some aspect of sort of data-driven modeling to your workflow, there are great tools out there. You never have to step foot in a lab to collect your own data to do this, right? So, I think some of the general advice would be try to, take advantage of the free tools that are out there. There are courses and, statistical algorithms that are really useful. There are courses on how to, work with something like Python, for example. I think a lot of classes computational classes for physical sciences tend to teach things like MATLAB and other things. I found Python to be very effective, but any way that you slice it, learning some aspect of how to, program things on a computer is going to be very advantageous. I think maybe taking a step back, one thing that I've found working with a lot of students who are sort of eager to use machine learning on their research projects. They have research projects and they're saying, hey, I've heard a lot about machine learning. I really want to use it. I think really sitting down and trying to understand what is the problem you want to solve, and is it applicable to machine learning first is the most important thing you can do, right? So while we've touched a lot about like machine learning for materials discovery, there are a lot of other applications that you can use machine learning for in material science. But if you're looking specifically at materials discovery, you might ask yourself, well, is this, we said this, a high dimensional problem, right? Are there multiple factors that control a variable that I want to know more about, right? Do I have data that describes this problem? Do I have the inputs and the output that actually describe the problem, right? If you're talking about, okay, well, I know fatigue strength is going to be controlled by a dozen different parameters, composition, structure, certain levers I can pull in the lab. But fatigue strength takes a long time to collect, right? So great, I have data to describe the problem. Great, it's a high dimensional problem. But is this something that I can easily verify if I do make a machine learning prediction, right? If it takes me a week to verify every prediction I make, well, in the span of a research program, you're probably going to, only verify a dozen or, less predictions, right? Who knows, right? Finding a way to find those surrogate properties that say, well, I can do, 3 hardness tests in a day. Okay, great. So now, you said, okay, I can actually verify a lot more predictions. Then I can go and take the next step and say, okay, this is a good problem for machine learning. Let's dive in.
I think that's a great warning, is that I know I was like this, is that I was like, machine learning is so cool, I want to do it right away. I'll just find a problem and like apply it to it. But some things really aren't that complicated that you need to do all these superfluous activities. I guess coming from my experience is that I am someone who is interested in data science and material science together. When we look at certain applications, I feel like you're a very broad, almost consultant with Citrine, where like people come to you with questions and like you try to help answer them. But if we look at like specific industries, do you think each specific industry, like batteries, like polymers, ceramics, are going to have their own expertise centers within like larger companies? Or how do you think that the way of the consultants is how most of these companies are going to kind of divvy up the work?
In terms of, do we think that every company is going to have a data science division, right?
Pretty much, yeah.
Or every materials developer is going to have data scientists. I think we've already seen that happening, and it just depends on how the organization is set up. And in terms of there were probably already people making those types of similar decisions, doing data-driven methods a long time ago, before sort of a lot of the popularity came about. Maybe they're just going to formalize those divisions more. I've only worked for Citrine, so I can't speak for a lot of other organizations. But what I will say is that we've seen that there are effective ways to use data in workflows to make new materials, and I think companies want to take advantage of that. Their biggest thing is sort of time to market, right? The faster they can get out something, the more advantage they're going to have in the market, right? If they can get out a battery that's 5% better, they're going to do it. So I think we're going to see, that however they slice it, they're going to want to pay top dollar to get that thing as fast as possible. And if machine learning is a way that they think they can do that, they're going to pay for consulting, data generations, their own data science division, whatever way to do it. Yeah.
True. And I'd like to add, David, we saw with our episode with Sally Klein that if there's not a data science division, then they encourage their material scientists to develop an expertise in some sort of data science fashion. So I think that could also be the next generation of material scientists, is there's that incorporation of learning, machine learning tools, for example.
Definitely. We've seen that the sort of dual skill set, understanding materials properties really well, understanding material science, being able to take that understanding and apply it effectively in a machine learning context is really, really important and critical if you want to do sort of materials discovery this way.
Cool. And David, I guess a question for you rather is, what sources or what resources have you used to learn more about ML, like since you've done this in the past?
I'm sure Chris would attest to this too, but the internet with where it is at today is fantastic. And there's so many things that people have built upon the shoulders of all this past human history, like modernizing all these different methods. So really, if you just Google something, it's like, I want to make a neural network, there are packages online where it has really long documentation about how exactly to set it up. I think that's honestly the best way, is just to try it out And there's so much help, there's so much documentation out there that it really is a very attainable problem that you can go out and try to solve yourself with like all the resources we have today at our exposure.
I totally agree. Yeah.
Cool. Well, thank you so much, Chris, for coming onto the show today. We really learned a lot about the integration of machine learning and AI with material science.
Thank you both. Hope it was insightful, and it was really fun for me. So appreciate the time.
Absolutely. Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. If you want to meet other passionate material scientists and engineers, join our Discord community using the link in the description. If you have any feedback for us, we would love to hear it. We want to grow this show with our community's input, so comment below with your thoughts on this episode and what topics you want to see us cover next. We'll see you very soon, and in the meantime, go change the world.